I will invite Xianwen to present.
Hello, can you hear me?
Yes.
Okay. Good afternoon. My name is Xianwen Hu. I am a PhD student from the University of Adelaide. My research topic is to use guided waves to evaluate the damage for the submerged structure. It is my honor to share my recent research outcome here. Submerged structures are everywhere, such as the water tank and the storage tank. These structures have plate-like components with one side exposed to water. They are vulnerable to corrosion damage. Corrosion can grow extensively in localized region and deteriorate the structure strength. It is important to inspect the safety of these structures so that catastrophic failure can be avoided. The existing non-destructive testing method for the submerged structure include visual inspection, acoustic emission, hydro test, and magnetic flux leakage test, and eddy current test. Generally, this method requires to pump out water and can only inspect a local region. For scanning a large structure, they are time-consuming and costly. My research is to use guided wave to improve the accuracy and efficiency of the inspection technique for the submerged structures. Guided wave testing is different from the conventional ultrasonic testing. The inspection area of the conventional ultrasonic testing is just a local area below the transducer. The transducer has to move along the surface to collect the data. In contrast, guided wave covers the total thickness of the structure over a fairly long distance. The inspection area is much larger. Therefore, the inspection using guided wave should be faster. Here is an example of the guided wave interaction with the damage. You can see wave scattering occurs as guided wave encounter the damage. And the location and extent of the damage can be evaluated by analyzing the features of the scatter wave. The majority of the studies on the guided wave application has been focused on the structure that are placed in the air condition. Only a few studies were conducted on the submerged structures. However, there is a challenge. When the structures are submerged in water, water can absorb the wave energy. Here, for example, here compares the measured guided wave signal from a water tank when it is empty and when it is filled with water. It can be seen that the guided wave signal measured from the water-immersed tank is much smaller than that in the case of the empty tank. This phenomenon can make it very difficult to detect the damage-induced wave. Here is the summary of the research literature paper on the guided wave in the submerged structure. Most of these studies were conducted on through experiment. They were limited by a small number of measurements. They only measure either the reflected signal or the transmitted signal. The scattering characteristic in other direction was not considered, but they will provide important information about the damage. Therefore, the objective of this study is to enhance the understanding of guided wave propagation on the submerged structure and to study the interaction of guided wave with the corrosion damage. The most sensitive feature will be identified, and finally, based on the selected feature, a practical damage detection approach will be proposed for the submerged structure. Here we present the theoretical prediction of the guided wave in a one-side water-immersed plate. As shown here, the bottom surface of the steel plate is in contact with water. The boundary condition of the top and the bottom surface are different. Traction-free boundary conditions apply to the top plate surface that is open to air, but at the water plate interface, the displacement and the stress in the out of plane direction are connected, but shear stresses equal 0 because water cannot sustain shear force. The behavior of guided waves depend on the excitation frequency and the plate thickness. The relationship can be described by the dispersion curve here. And within the selected frequency thickness value, there are three wave modes. They are fundamental leaky symmetric wave, and the fundamental leaky anti-symmetric wave, and the quasi-short wave. The quasi-short wave represented by the black line can only exist for the submerged plate. And this wave travel along the water plate interface, and at given frequency thickness value, quasi-short wave has the smallest phase velocity and the lowest attenuation. Smaller phase velocity means this wave mode has a shorter wavelength and hence have higher sensitivity to the small damage. For this reason, the quasi-short wave is selected for further study in this project. And to simulate the guided wave propagation on the one-side water-immersed plate, Abacus is used to develop a 3D FE model. There is a 2 mm thick steel plate, and the bottom surface is in contact with water. The red circle on the top surface represent the location of the guided wave actuator, and here is the excitation signal. The frequency is selected at 100 kilohertz. Here is the contour plot of the simulation result. On the plate surface, you can see there's only one wave mode. There's only one wave packet, and this wave packet has a flexural shape, and the most of energy is confined to the water plate interface. For this feature, this wave mode is recognized as quasi-short wave. The leaky fundamental anti-symmetric and symmetric wave are too weak to be observed. And the simulation result is verified through the experimental measurement. Here is the experiment setup. A water tank is designed with the front wall being the test plate. During the test, the tank is filled with water so that the inner surface of the plate is in contact with the water. Here compares the experimentally measured signal with the simulated signal, and the phase velocity was calculated for the frequency range from 70 kilohertz to 150 kilohertz, and you can see we compare the simulation result with the experimental measurement and also the analytical dispersion curve. There is a good agreement. Therefore, the simulation result of the submerged intact steel plate can be verified, and the measured signal are confirmed to be the quasi-short wave, the interface wave. Then after that, a circular blind hole was created at the water plate interface. The blind hole is a simplest representation of a corrosion pit, and here is the simulation result, and the measurement was taken at 36 points on a circular path around the damage. And another verification experiment was conducted, and the blind hole is drilled at the internal surface of the test plate, and the measurement was taken at the same location as the 3D FE model. Here compares the measured signal with the simulated signal. This is the top graph is the signal in the reflection direction, and you can see the incident wave and the scatter wave are separate from each other. The scatter wave are generated from the interaction of the guided wave with the damage, and the bottom graph is the signal measured in the transmission direction as represented here by the yellow circle. And the polar plot at the center summarize the peak amplitude of the all measurement signal. There's a good agreement between the simulation result and experiment result. After that, the experimentally verified FE model is employed in parametric study to study the scattering characteristic of quasi-short wave at blind holes with different dimensions. And here is the dimensions considered in the parametric study, and the scatter wave were extracted by baseline subtraction, and the scattering directive pattern was constructed to show the amplitude of the scatter wave in all directions. And here is the typical example of the scattering directive pattern of quasi short wave at different blind holes. The depths of the blind hole are fixed at 0.5 millimeter, but the diameter are different. You can see the scattering directive pattern depend on the size of damage. Further investigation, we fix the depth of blind hole first, and we can see the amplitude of the scatter wave in the transmission direction increase with the size of the damage, but the amplitude of the scatter wave in reflection direction, they fluctuate significantly and following a sinusoidal pattern. The red line is the scattering pattern that is in the direction parallel to the incident wave, and they have the largest scattering pattern, scattering amplitude. And the black line is the scattering amplitude that is in the direction perpendicular to the incident wave. They have very negligible amplitude. This indicates that sensor that placed at the direction that is in direction perpendicular to the incident wave, they may not be able to send in the damage-induced wave. Then we fix the diameter of the damage. And we can see the scattering amplitude in both the transmission and the reflection direction. They increased with the depth of the damage, and in the deep damage, the scattering amplitude that in the direction perpendicular to the incident wave have comparable amplitude to the scattering wave in the reflection direction. Here we can see that the scattering pattern of quasi short wave are very sensitive to the hidden damage in the submerged plate, and the scattering pattern can provide a information and a guideline for the placement of the sensor. Based on the findings of this study, my future research is to develop a practical approach that employs the scattering patterns to locate and evaluate the corrosion damage on the one side water-immersed plate structures, such as the water tank and the pipelines. And yeah, that's the end of my presentation. Thank you.
Thanks, Xianwen, for your interesting presentation. So the comments and the questions from audience.
Can I ask a quick question?
Yes.
Yeah.
A bit technical. So this is a good research, and you've made good progress. Congratulations. I guess my question is, have you considered, or are you going to consider multiple defects on the same structure? Because in real, like water tanks, as you know, for the ones we are going to inspect, they are aged and not in good shape anyway, and you got deposits at the bottom, you got corrosion, on the sides. It's not a clean plate with one defect. So is it going to be part of your research, or have you considered that?
Yeah, this will be considered in my future research. This is my first paper, and it's only a fundamental study to study the sensitivity of the quasi short wave for the damage. But my later research will further investigate the scattering pattern and start with the single damage, and then we'll move to the two or different shapes, and also the irregular shape of the damage. Well, I will consider that and incorporate that. Also, I will study more practical the placement of the sensor, because you can see for my presentation, a circular measurement is not practical in the real life, but this is okay for the sensitivity study. But for real application, I will consider more feasible configuration of the sensor.
Yes, okay. Just one comment. There's probably a demand. You probably know that already. There's demand from the water industry that you want to inspect the water tanks, the large water storage tanks, especially at the bottom. You know, on the side walls, they can do something, but for the bottom, it's very difficult for them to do anything. So what they do nowadays is to drain the tank and send someone into the tank and have some visual inspection, but they also have to clean up the deposits at the, you know, at the bottom of the tank. So if you can do something in situ, you know, without draining the system, because if you drain the tank, that means that you have to pull the tank out of service. Sometimes you don't really have the, you know, ability to pull the tank out of service. So, you know, if you can develop something, that will be very useful for this application.
Oh, thank you. That's very interesting, and if I have enough time, I will definitely consider that, because this will have two different medium on the plate. One is the liquid, the other is like a solid. So the soil may consider in solid in many papers. So I think this is a very interesting extension of my this study.
Okay, thanks, Xianwen. Concern time.